Hey everyone. So in the last video, we went over a little bit about a pulley problem, and I realized we haven't done a video on rotational motion. And it's super important to understand and kind of conceptualize. I know it can be pretty tricky to get it under your belt. But for instance, a lot of the times with a pulley problem, instead of being asked about the forces acting on the pulley or the acceleration of the system, you could also be asked about the movement of the pulley itself, which is a completely different piece. So when we have circular motion, we have this nifty trick that we can use to convert between translational motion and regular motion. So we're given S, which is our distance around a circular path. So you can kind of think of it as a segment like this, or an arc length is usually how it's conceptually called. We have S equals theta R. Theta being the angle that you travel. Um, and r being the radius or the distance from the center. And the same thing also applies to velocity. Velocity is equal to, and don't confuse s with speed. It's not speed, it's arc length. Um, and velocity is the same thing as omega times r. Omega being our angular speed in radians per second. That's essentially how fast we're traveling in this circular path. And it's in terms of our circular motion. Then, of course, we have acceleration is equal to um, alpha, which is our angular acceleration, and r. Now, don't be confused with alpha and centripetal acceleration. These are two different things. These are not the same. Um, our alpha is in terms of radians per second, and our centripetal acceleration is a linear force. Now, it's something that you can write, um, and it actually, the vector points towards the center. Um, if you have, for example, if you have like a object on a string that you're twirling above your head, the um, the magnitude of the acceleration points towards the center, whereas the velocity um, is perpendicular to that. That's our tangential velocity. And the direction of the tangential velocity will always be changing um, as the force from the acceleration pushes it in. So it's a kind of an interesting relationship that we have. Now, we want to be careful that we don't mix these things up. Um, this is a whole different kind of beast. We'll tackle this later. But for now, we're going to focus on rotational motion. For the example in the last problem that we did, we talked about a pulley. So, what are some other equations that we can use that help us to understand conceptually what's going on? Um, Force in terms of rotation is known as torque, written by the Greek letter tau. T equals RF or force, and it also matters what angle you're applying it at, sine theta. So, for example, let's say you have a wrench and a bolt, kind of like this. It's a pretty bad drawing. You'll have to forgive me. Um, it matters the distance that you are from the center of rotation, r. So r would be, for example, how far you apply the force. Say we apply force towards the center right here. Our r is going to be that span from the center of rotation to where we apply the force. And our force vector is um, going to be where we apply the force and what direction. So in this instance, it's perpendicular to the radius. And the theta is the angle between the force and the radius. Now, sine of 90 is 1. So in this instance, our torque would be RF. But what if it's applied at an angle? That's when things kind of change up a bit. So that's when we need the sine theta to describe the force that's being applied. And again, the theta is the angle between the applied force and everything. So torque is super important to remember, super important to keep in mind. There will be a lot of problems involving torque. So going back to our example from the pulleys, um, if we have two different masses, let's say we have a smaller cylinder, mass M on this side, and we have a larger cylinder, mass capital M on this side. Using our intuition, we know that the acceleration is going to be um, clockwise. Mass M is going to accelerate downward, and mass little m is going to accelerate upward. And so we want to choose one direction or the other to be our positive direction. And because it's a lot easier to choose the positive direction than the direction of acceleration, we're going to choose this side to be positive. Clockwise is positive, and counterclockwise is negative. Now, sometimes in a problem, they'll tell you which direction is positive and which direction is negative, but a lot of the times they leave it up to you. So, in the last problem, we talked about the forces being applied. And um, let's say, we already have an equation that we've derived for our forces. We have, um, let's see, we have force one um, that's acting. Let me draw a new diagram right over here. We have force one acting here on the pulley. And then force two acting on the pulley. And so um, in order to figure out things like this, we need to set up an equation using Newton's second law. And if you remember Newton's second law, F equals ma. The force equals mass times acceleration. But because we're dealing with rotational motion, um, more often than not with pulley problems, you'll need to find things in terms of rotational motion. So using some of our equations that we have here. Um, so we need to write um, things in terms of torque. So we can write it as this. The sum of all the torques is equal to um, our angular acceleration times our moment of inertia. Now, this is just a fancy way of saying rotational mass. What the heck does that mean? Our moment of inertia is basically how much a mass resists rotation. So we're given this equation for general bodies of mass. And again, this is a um, oversimplification. A lot of the times, the you'll usually be given a moment of inertia. Um, but if we're being technical and we want to be completely right here, we'll actually write it as an integral or the sum of all the moments of inertia. But for simplicity's sake, we'll leave it as this. I equals mr squared. So what does this mean? This tells us the mass and how far apart it is from the center of the mass. Now think about if you've ever seen an ice skater leap into the air, um, and when they're spinning, they pull themselves in. Why is that? Because they pull themselves in, their mass is closer to them, so that R that they have is much smaller, which means um, that there's a smaller moment of inertia. So what that means physically is that the forces, if the moment of inertia goes down and torque stays the same, that means that naturally our angular acceleration is going to go up. And if you haven't tried it, if you have a spinning chair or something at home, or if you have weights, I'm sure you've seen this demonstration before, try holding the weights out as you're spinning on a spinning chair or something or merry-go-round. And then as you pull things inward, notice how much you accelerate or go faster. And so that's basically what this is telling us. Um, and because it's rotating, it matters how far you are um, from the center of mass. So we'll use this I equals mr squared. So this is our equation, our mass flow equation that we're going to work with, but we don't have any values that make sense that are according to our givens. Now, in the last problem, we figured out the forces acting on the pulley. So we could say that we're given um, force one and we're given force two, and the masses of the each of the masses were given in the previous problem. So we can say that we're given those also. Okay, so what should we do? Now, with the torque, let's see all the forces that are acting on the pulley. We have F1 in the positive direction. Remember, we chose clockwise to be positive this time around. And F2 being negative in the negative direction. And because it's a pulley, notice that it's tangential to the radius. The force is tangential to the radius. Now, um, sorry, excuse me, not tangential, it's perpendicular. Now, because sine of 90 equals 1, we can simply write our torques as R equals uh, as RF, as the radius times the force. You'll also very commonly be given the radius in problems like this. So let's write the sum of all the torques. We have um, R F1 minus R F2. Now, because it's going in the negative direction, that's why we're subtracting it. It's going counterclockwise. And doesn't matter which direction you choose with, it's a lot easier to go in the direction of acceleration, but you want to make sure that it's consistent one with another. Then our alpha um, is going to be here, and then because we have I equals mr squared, or a moment of inertia, we'll write it as the mass of the pulley. Remember, this isn't the the mass of the weights. This is the mass of the pulley. So let's write it. We're also usually given the mass of the pulley. I'll write it as m sub p. So this is going to be m sub p r, which is the radius of the pulley squared. And from here, it's pretty easy to um, go ahead and simplify. We can divide both sides by an r, and usually they'll ask you for the angular acceleration of a system. That's usually what we end up solving for. So when we solve, we get F1 minus F2 all over the mass of the pulley, MPR equals alpha. So this is what we get. And they might do something goofy like ask you for omega or the angular velocity. And we can essentially use our kinematics formulas that we learned earlier. They apply exactly the same to our angulars. So we can get our omega final equals, let's see, we can do omega final equals omega initial um, plus the acceleration and the time. And usually if they're going to ask for the omega, they'll give you something like, okay, the pulley is starting from rest, so our omega initial is 0. And remember, the units are different. It's radians per second. Anyways, hope that helps. I know these physics equations can be a little bit tricky, but they're not too bad once you simplify them, and once you really drill in what you're working with. So keep on crushing it, and I'll see you later. Bye.